Hello, everybody. I'm Jon Peddie from Jon Peddie Research. I think many of you know me. We specialize in computer graphics, visualization, various forms of reality, this being one of the tests of reality. We do consulting for industry leaders and investors. We write reports on hardware and software. We do product testing, and we also do some conferences. The major takeaway points will be ray tracing isn't new. You know that, or you should have known that. Ray tracing will save time and money. Imagine you didn't know that. Ray tracing is or should be used throughout the pipeline. Ray tracing, real-time ray tracing, is real, no joke. And ray tracing makes everything more immersive, and that's going to be one of the major takeaway points. So just a little historical background. Arthur Abel was probably the first guy to use ray tracing by engaging a computer. And he did it to illustrate nuclear vulnerability in tanks. He wasn't really trying to generate a photorealistic image. He was trying to show how computer analysis could be used to reveal the nuclear vulnerability of armor tank to gamma rays. But it was an example of, or the first example of ray tracing. Ray tracing has been said to be computationally impossible. And unfortunately, I didn't hear all the previous speakers' presentation due to my technical difficulties. But in any case, he may have already said this. Ray tracing will just keep on running and running and running until you tell it to stop. And so you do that, you make that decision of when to stop. It can be done arbitrarily at a number of seconds or a number of frames or a number of rays, but you do it on a trade-off, basically a point of diminishing returns. And so you're looking for good enough versus great. Ray tracing's computational time is due to its content. It is content dependent, and it is time dependent. And so if you look at this picture, you can see three examples of the progression of ray tracing going through, and you might say the lower right one was the best. It's still pretty cruddy. You can do better than that, but it's a user's choice. Ray tracing is real, and it's real in a variety of ways and places. AMD has done it in consoles. Asher, who will be speaking a little bit later, did it upside down, and they'll explain that. Imagination has developed a thing called ray coherency, which has made it more efficient for mobile devices. NVIDIA, as you've just heard, does AI and special cores. And Silicon Arts, I don't think they're presenting, but Silicon Arts has blended a SIMD architecture with a MIMD architecture. I can deal with that on Q&A, the SIMD, MIMD, if you're not familiar with those terms. So we have multiple choices. We have multiple platforms. We have ray tracing now on consoles. We have it on notebook and laptop PCs, we have it on workstations, and we have it on mobile devices. And my prediction is that in less than 5 years, all games, CAD, simulation, and visualization will be using real-time ray tracing. And you got to ask, well, why not? Why wouldn't you do it? Because for one thing, it saves time and it saves money. And I'll explain how that works in just a second. So ray tracing saves time and therefore money, primarily because you can now stop doing all of the coding that was necessary to make fake graphics. In the past, we had to do that because the computational load for doing ray tracing was so severe that we just couldn't afford it and get a reasonable picture in a reasonable amount of time. We've now overcome that in a variety of ways, as I mentioned in my previous slide. And so we can now stop doing all that coding. So whereas we used to have to write a lot of code for shadows or for reflections or things like that, which, by the way, was inaccurate, ray tracing now does that. It does it fast and at almost no cost, and it's perfect. So ray tracing saves my time and money because programmers no longer have to struggle with the shadow and reflection maps and trying to save a couple of frames a second by using fake graphics. Also, ray tracing is scalable and mungible. If you change the model or move it or do anything to it, you don't have to go back in and do a lot of recoding. Ray tracing will correct automatically, and again, it does it perfectly. So this greatly reduces the number of patches to a game or something like that, and it totally eliminates any cracks that might appear in the model. Most designs today are using 3D modeling, and all of those models move. Even a stationary building moves relative to the sun, as do the reflections and shadows. And one of the great examples of that is a building that was built in London, went up in 2014. It's called, and it's some people call it the walkie-talkie, other people call it the death ray. The people who built that building, the architects and so forth, chose not to use ray tracing. And had they used ray tracing and done a proper environmental test, they would have found out that the concaveness of that building does indeed create a sun ray that floats around the city as the sun is moving. And at a certain particular moment, there was a car, unfortunately, parked in a spot where that ray concentrated, and it melted the dashboard of it. And so I don't know what they've done to fix that, maybe diffuse the glass or something, but the point is that they would have known that before the building was ever built had they used ray tracing. And it's just a perfect example of how ray tracing can help you through the entire pipeline, which I'll get to in just a minute. So ray tracing, as I mentioned, saves time, saves money. The final images are tuned up and constructed in, or typically final images are tuned up and constructed in compositing, which is basically laying of layers of images. You still can do that with ray tracing, and in fact you do, but you can eliminate a lot of those layers because the images are so perfect to begin with. Also, you don't need any special computer graphics tricks, as I mentioned, so therefore you don't need any time-consuming and expensive programming, sorry. So ray tracing, as it's used for animation in games and other things that may not look real or behave correctly according to gravity, but the light on them behaves correctly. And so that's an important point, because a lot of people say, well, yeah, ray tracing is great for architectural buildings and for automobiles and various other product designs and so forth, but not everybody wants to see reality. But if you think about the animations, the really great animations that have come out of Pixar and other companies, those are ray traced images. And just because the characters in them and the worlds in them are not actual, the lighting is. And that's the big takeaway I want you to get from this, is that the lighting is everything to our brain. If our brain doesn't perceive the correct lighting, then we just can't deal with what we're looking at. Here's an example of the pipeline, and when I talk about the pipeline, I'm talking about the various steps from concept to manufacturing. This is a nice building slide. Sorry, you're not going to get to see that, but in any case, if you look on the left, you see a picture of the building. That is the World Trade Center and 9/11 Memorial Museum, and that's a representation of it, a modeled representation of it that was done in 2006. This particular project was one of the first to use ray tracing through the entire pipeline. And so they used it in the concept for that model that you see on the left. They used it throughout the design process. And the reason that was valuable and important is because any design, doesn't matter what it is going to hit some type of a hurdle, some type of a problem, and need to make some type of an adjustment. And because they started with ray tracing and worked all the way through it, those adjustments were made and still were able to maintain the original fidelity of the design. And that was critical to a lot of people involved in this emotional site. He also used it in virtual manufacturing, and I have a great example of that coming up, where you actually build the thing in the computer before you actually build the thing. And then, of course, you use it in marketing. Marketing has been probably one of the first and foremost examples of where ray tracing would be used because automobile manufacturers, for example, make ray tracing views of their cars before they build the cars to get consumer reaction to them. So this is the way it'll be done from now on, I think. And where it's done is almost not important. It can be done on a local system. It can be done in a hybrid local cloud system or done totally in the cloud. One of the best examples of it is Honda. Honda's been a pioneer in this. And Honda was the first one to build, that I know of anyway, first one to build an all digital car, which is known as a digital twin. And it's basically a replication of what the real thing will be or will become. Using ray tracing, finite element analysis, and a game engine, Honda crash tested that car before a single part had ever been manufactured. And there's a really great video about that. I meant to put the link in, but I ran out of time. My email address, which will show up at the end, if anybody wants that Honda video link, just send me a note and I'll get it for you. But anyway, they did that. They crashed the car. And in doing so, they discovered, as a result of being able to use ray tracing, which parts were behaving and bending and, you know, failing in which way, and what they had to do to reinforce those parts or redesign the system so that they wouldn't get bent. Later on, Honda built a car, and as protocol requires, did actually crash a couple. And they found out that they got better results with the virtual testing because, for one thing, they could keep on doing it until they got it right. Can't keep on crashing cars. They could run it backwards, and they could run it in slow motion. And that was a tremendous benefit for them. And they learned so much, and they saved so much time and money as a result of it. Also, there was no mess to clean up later, so that's another benefit. So will real-time speed up things for us? It absolutely will in games. It may not for everything else, but not because of the inherency of ray tracing speed, but because of a thing called Blin's law. And Jim Blin, a world-famous computer graphics mathematician, came to the conclusion that rendering time will pretty much remain the same regardless of what the performance characteristics of your hardware and your software are. And the reason for that is because we just want to make beautiful pictures. We want to make better and better images and so forth. And if we can get a few more cycles, we'll use them, even though we might burn up the same amount of time as if we didn't have those cycles. But the thing about it is, ray tracing makes things look real, beautiful and physically accurate. And that's really important because it makes it believable. Even if it's a fantasy movie or a superhero in a game, in a first-person shooter, for example, a viewer, any human, can tell immediately if things don't look right. And if they don't look right, you stop believing what you're looking at and you get distracted. You look at the thing instead of the story. So ray tracing gives you an emotive, an immersive, and subliminal experience, and it's hard to get across sometimes that it's difficult, if not impossible, to really quantify ray tracing. You can say you get more frames per second, or you can say you can use higher screen resolution, color depth, and so forth. But our brain senses ray tracing more than we can measure it. So when the image stops being a distraction, when the image doesn't have, I should say, artifacts in it, and we don't look at the image, then it becomes immersive. And then the story flows. And then we feel it. We actually feel it more than we see it. So I think this might be my last ray tracing talk. I think that ray tracing is going to become so common and so pervasive and so ordinary that it'll just be expected to be there, just like we expect a color monitor to be there and expect them to have high resolution. So what have we learned? Well, we've learned that ray tracing isn't new, but you of course knew that. Hopefully you've learned that ray tracing will save time and money. You should appreciate that ray tracing is, or should be at least, used throughout the pipeline. Also that game engines and FEA and ray tracing are the ultimate virtual prototyping partners. They just go hand in glove. And that ray tracing will be felt and sensed more than it is measured. So ray tracing is real, it really is. And this is my last and closing slide. And it's too bad I lost the animation because that ball that you see in the center there bounces and makes a big splatter, and bounces and makes a big splatter. And it was just fantastic. Anyway, that's it. That's the overview. Hopefully it worked, and hopefully we can get the rest of the seminar going.
We might have time for just a couple quick questions. If anyone has a question to add.
These slides will be available. M2 will distribute them to you, and or they'll be on our webpage. So if you find something interesting in them and want them, they're open to you.
Great. Yes. Okay, wonderful. That was great, Jon. Thank you so much. Glad we were able to get you in there.
Yeah, got some of it working.
Yeah. Remy has a question. Who is number one?
I am. But he already knew that. Number one, what?
I don't know.
Well,
I don't know if he can hear.
Be a little more explicit, Remy.
He hasn't said.
Okay, well, if he's trying to find out who's the number one ray tracing, what should I say, hardware guy, that's clearly NVIDIA, no question about that. If he wants to know who is the number one ray tracing software company, in my opinion, I think Asher is going to get that, and you'll hear their story in a little bit. But all the companies involved who are involved in ray tracing bring something to the party, and I don't think we need to have a best or a winner or anything like that, and therefore have losers. I think everybody is pushing this way, or pulling this wagon, I should say, and we're all going to be beneficiaries of it. Everybody's making a contribution, and they all learn from each other. So NVIDIA does something, AMD and Qualcomm learn something about that, and then Qualcomm does something, and the rest of the gang learns about that, and so the whole thing just keeps moving forward. It's not a winner or loser type situation.
Okay, great. There are some more. There are some more questions here. Maybe we could just take one more. Blind's law was a rendering time won't change, but is that not what real-time ray tracing is, the likes of Unreal is aiming to do? Actually that, changing rendering time, or maybe I misunderstood the point.
No, it's a good point. It's a debatable thing. It's one of those philosophical conversations that you can have with your friends about it. Blind's original observation was relative to the movie industry, and the idea was, what can we do to get movies made more faster? And the answer was, you can't. It just takes, it seems to take a finite time. With regard to Epic's ray tracing and game engine, or Unity's ray tracing and gaming engine, they do indeed speed up things. In fact, remarkably so. And that will improve two things. Number one, it'll improve the creation time for game developers to get their game developed, but it'll also improve the playing time for the gamer. And so in that case, Blind's law kind of gets pushed to the side, doesn't really become applicable in that particular situation.
Great. There was one, let me see. There's another question from Lena. Does ray tracing require special powerful hardware, or will it be on a MacBook Air, for example?
Well, yes and no. You can do ray tracing on any CPU. It's just a question of whether you have patience to wait for the picture to get built. If you want real-time ray tracing today, the only available solution on a PC is on a PC, and that's using NVIDIA hardware. Now, Azure, as I mentioned, is going to tell you in a little bit that they can do it real time on a mobile device, a variety of mobile devices, and that's correct. I've seen all their demos now, and I think a lot of other people have as well. The difficulty is, as far as I know, and Azure will address this better than I can. I don't know of any applications that have engaged Azure software yet, so that we can go out and actually, we as consumers can go out and actually use it. So the only consumer available solution at this exact moment is NVIDIA's ray tracing boards in a PC.